In this video, we are going to review the paper, the first M87 Event Horizon Telescope, Results 1, the shadow of the supermassive black hole. This paper was received in 2018, March 1, and the authors explain in the abstract a resume and schedule about what is the objective of this paper, and explain us a little about the Event Horizon Telescope, about the wavelength of this resolution of this telescope, and the object of interest in this case is M87, and some results. For example, the authors tell us that they have resolved the central compact radio source as an asymmetric bright emission ring with a diameter of 42 microarcoseconds. Tell us that the mass of this object is 6.5 times 10 at 9 solar masses. In the introduction, the authors explain about what is a black hole. They tell us that this kind of objects, there are a fundamental prediction of the theory of general relativity predicted for Albert Einstein in 1815, and this object has event horizon, and Penrose in 1965 tell us that the production of black holes is generic in general relativity. Stephen Hawking in 1976 explained us that the heart of fundamental question in unify general relativity with quantum physics in the study of black holes. The black holes, there are many kinds of black holes, but the black hole of M87 is a supermassive black hole, and this is a kind of active galactic nuclei. What is a active galactic nuclei? And M87 is a galaxy, and this galaxy has in the center a supermassive black hole, and has two accretion disk around the black hole, and torus and jets. This object has two jets. This is an image. The first image was captured for Hubble Space Telescope in the band of optical. The second image was registered for ALMA in the frequency of 213 GHz. The third image was captured for very large baseline array in the frequency of 23 GHz. And finally, we have the central image of this object, M87, in the band of 230 GHz. This is active galactic nuclei, and this object has a torus. This is the torus. Is more or less a distance, or 1 parsec of distance to the black hole, central black hole. The black hole has a dimension of 10 at -5 parsecs, The jet has a dimension of kiloparsecs, and the disk, accretion disk, has a dimension of 10 at minus 3 parsecs. There are some regions close to the black hole too, the broad emission line region and narrow emission line region. These zones are important because in this zone there are gas and dust, and we can see the optical properties of these objects. If we see the jet directly, the active galactic nuclei regularly, the name is a blazar. If we see this object not directly, with inclination, the name for this is quasar. The kind of this is FR2 or FR1. If we can see the jet, the name of this is the kind of radio loud. If we can see the jet, the name is radio quiet. Okay, the authors tell us that this is M87 is an active galactic nuclei, and these have a central bright regions that can outshine the entire stellar population of the host galaxy, and tell us that these objects can be a quasar, for example, and these quasars are the most luminosity steady sources in the universe. This AGN, active galactic nuclei, has a collimated relativistic plasma jets. This jet, or this, the dimension is of kiloparsecs. This collimated relativistic plasma jets is launched by the central black hole and contribute to the observed emission. And this emission may be produced either in the accretion flow. And the black hole has a photon capture radius, RC. It is the root square of 27 Rg. Capture radius is square 27 Rg, and Rg, it is gravitation radius. It is gravitational constants mass divided 4c to square. Then it is this constant multiplied by gm divided for the velocity of light to square. And it is important because the photon capture radius is larger than the Schwarzschild radius. It is that marks the event horizon of a non-rotating black hole. It is Rs is 2 gravitational radius. This is 2 times gm between divided CS square. The authors tell us that there are a parameter impactor, parameter of impact, and tell us 3 scenarios that if B is greater than R is, is captured radius. The second scenario is B is equal to capture radius, or the third scenario is B is less than RC. In this case, tell us that the photons are captured and plugged in to the black hole. In this other scenario, the photons, when B is equal to RC, the photons are captured too, but they will be in a circular orbit. And finally, the third scenario, it is when B is less than RC, greater than. This is in this case, the photons escape to the infinity. This scenario is interesting because the photon form a photon ring around the black hole with this radio. You'll see that this radio is exactly this. Is the constant of gravitation, the mass of black hole, the speed of light, and this other constant. For this paper, the authors study the simulation of luminet that present the first image of a black hole in the paper of 1979, and now for Event Horizon Telescope, the authors in this experiment use a very large baseline interferometry with this frequency 20-30 gigahertz, that it is equivalent to 1.3 millimeters. And with this resolution, the authors resolve that the central mass of the black hole, and Sagittarius A. They explain us that with 1.3 millimeters and shorter wavelengths, the baseline interferometers achieve an angular resolution sufficient to resolve the shadow of both sources. The two sources, it is Sagittarius A and M87. The authors tell us that in this paper, present and discuss the first event horizon scale image for the supermassive black hole candidate. It is M87 and with these wavelengths. In the second part of this, the authors explain about the radio core in M87. Curtis in 1918 detected a linear feature in M87. This morphology was called a jet, and this jet in 3C274 extend out 65 kiloparsecs and with a power about 10 at 42 to 10 at 45 ergs seconds at -1. And it's well studied in the optical, X-rays, and gamma rays band. The radio structures of large-scale jet was studied for this author, Owen and Gasparin, and the core of M87. Explain us that the very large baseline of interferometry observation with wavelength revealed a diameter of emission region approximately to 40 microarcoseconds and resolved that the distance of M87 it is of 16.8 more or less megaparsecs, and infer that the mass to be 6.2 times 10 at 9 solar masses. In the third part, explain us about the Event Horizon Telescope and tell us about the participation of this experiment. In this map, we can see that there are one telescope here, other here, other here, here, and it is a bigger plate of a telescope with several antennas inside. From Chile to Mexico to Hawaii to Spain. The participation was formed from Atacama Large Millimeters of Millimeters Array, it is ALMA, Atacama Pan-Finder Experiment Telescope, APEX, Large Millimeter Telescope, Alfonso Serrano, in Mexico, the IRAM Telescope on Pico Veleta in Spain, Submillimeter Telescope Observatory in Arizona, James Clerk Maxwell Telescope, and Submillimeter Array in Hawaii. And South Pole Telescope in Antarctica. With this baseline interferometry, the range was from 100 160 meters to 10,017 kilometers. This instrument is working with radio observations in radio frequency. Then this data needs correlation and calibration. The M87 was observed from April 5 to 11 in 2017 April on, and the authors tell us that the weather was uniformly good to excellent in these days, the days of observation, and the number of scans obtained per night ranged from 7 to 25 as a result of different observing schedules. This is the map in coordinates UV. It is coordinates in Fourier transform, and this is the observations from different telescopes, ALMA, SMT, APEX, etc. And the radio is to 25 microarcseconds or 50 microarcseconds. This plot is show us about the calibration and the correlation about the antennas. The flux density was registered in Jansky, and the median scan average was the signal noise ratio was greater than then. And these coordinates U and B, the authors explain us that the final calibrated complex visibilities UV correspond to the Fourier components of the brightness distribution on the sky at the spatial frequency UV, determined by the projected baseline expressed in units of the observing wavelengths. The image of this experiment was explained in this part of the paper, and the authors tell us that they explored two classes of algorithms for reconstructing image. One of these is clean and RML. RML means regularized maximum likelihood. And this is the result of the observation, but the explain with more detail is in the other paper, not in this. But in this explain us about a little about the software that the teams use for this. The image was blurred The image has a filter with a circular Gaussian with a conservative angular resolution of 20 microarcseconds. This blurred is this effect, like not knitted. The theoretical modeling is the part 6. The authors explain us about the simulations, and the numerical simulation was used for general relativistic ray tracing and radiative transfer code is. And tell us a typical general relativistic magnetohydrodynamics simulation in the library is characterized for two parameters. The dimensionless spin, it is Gc divided by Gm squared, where G and M are the spin, angular momentum, and mass of the black hole. And the magnetic flux over even horizon, it is where this letter and M are the magnetic flux and the mass flux or accretion rate across the horizon. These parameters allow us to describe accretion disks that are either prograde when the A is greater than 0 or retrograde when A is less than 0 with respect to the black hole spin. And we have a standard and normal evolution. It is a sine with phi is more or less 1, or magnetically arrested disk, it is a mass. In the experiment variant A and phi, we have performed 43 high-resolution, three-dimensional, and long-term simulation covering well the physical properties of magneticized accretion flows onto curved black holes. Tell us too that all general relativist magnetohydrodynamics simulation were initialized with a weakly magnetized torus orbiting around the black hole and driven into a turbulent state, but by instabilities including the magnetorotational instability. The authors too tell us about some characteristics. Tell us about the first is the observed image is consistent with the hypothesis that it is produced by the magnetized accretion flow orbiting without a few gravitational radius of the even horizon of a curved black hole. Curve is a black hole with rotation. This is the reason because we need to use this parameter A, prograde or retrograde. Second, the north-south asymmetry in the emission ring is controlled by the black hole spin and can be used to deduce its orientation. The third thing is adopting an inclination of 17 grades between the approaching jet and the line of sight. The west orientation of the jet and co-rotating this model, matter in the bottom part of the image is moving toward the observer. Clockwise rotation, as seen from Earth, And this is consistent with the rotation of the ionized gas on scales of 20 parsecs. It is 7,000 gravitational radius. Finally, tell us that the model with this parameter a equal to 0 are disfavored by the very conservative observational requirement that the jet power be with this energy. For more induced models that produce a sufficient powerful jet, it is powered by extraction of black hole spin energy through mechanism to the akin to the Blankford-Sandek process. The seventh part of this paper explain us about the model comparison and parameter estimation. Tell us that they use two distinct Bayesian inference algorithms and demonstrate that such crescent models are statistically preferred over other comparable complex geometric models that we have explored. This is the image, and the blurring, the effect of blurring, it is effect at not focus than this. This is a parameter for M87. With the experiment, the authors found that ring diameter is 42 more or less micro arcoseconds, ring width less than 20 micro arcoseconds, axial radio is less than 4 to 3. The mass is 6.5 times 10 at 9 solar masses, etc. In the discussion, the authors tell us in the first place that our analysis has used multiple independent calibration and image techniques, as well as 4 independent datasets taken on 4 different days. Second, the image structure matches previous prediction well. Third, because our measurement of the black hole mass in M87 is not inconsistent with all of the prior mass measurements, which allows us to conclude that the null hypothesis of curve metric, namely the assumption that the black hole is described by curve metric, has not been violated. 4. The observed emission ring reconstructed in our image is close to the circular with an axial ratio. With this ratio. Similarly, the time average image from our general relativistic magneto-hydrodynamic simulations also show a circular shape. In the conclusions, the authors tell us that they find the image to be dominated by a ring structure of 42 more or less micro arcoseconds diameter that is brighter in the south. The black hole mass is 6.5 5 times 10 at night solar masses, and in the future, future observations and further analysis will test the stability, shape, and depth of the shadow more accurately. Another primary Event Horizon Telescope source, Sagittarius A, has a precisely measured mass 3 orders of magnitude smaller than that of M87. Finally, in conclusion, they have shown that direct studies of Event Horizon shadow of supermassive black hole candidates are now possible via electromagnetic waves, thus transforming this elusive boundary from a mathematical concept to a physical entity that can be studied and tested via repeated astronomical observation. In this project participate CONICIT in Chile, CONACYT in Mexico, the National University Autonomous of Mexico, UNAM, etc. Okay, finally we have the authors. There are hundreds of authors. 100. I hope this video can help you, and I see you in the next video.